Welcome to a future that arrived too early. These machines were smarter than their time, too advanced, too bold, too different. Farmers didn't understand them. Industries weren't ready. They weren't failures. They were mistakes in timing. Number 1. Fordson E27N, roadless half-track tractor, 1940. In the years immediately after the Second World War, European agriculture faced conditions that ordinary tractors simply could not handle. Vast areas of land had been churned by military vehicles, drainage systems were damaged, and heavy clay soils remained waterlogged for long periods. Conventional wheeled tractors struggled in such environments. They sank, spun, and wasted power. British engineers at Roadless Traction Limited saw a solution in adapting proven military ideas for civilian farming. Using the Fordson E27N tractor as a base, they replaced the rear wheels with continuous steel track units, creating the Fordson roadless half-track. The result was a machine that combined the familiar layout of a farm tractor with the ground-gripping ability of a tank. Technically, the roadless conversion was superb. The tracks distributed the tractor's weight over a much larger surface area than pneumatic tires, dramatically reducing ground pressure. This allowed the tractor to work on soft, wet, or newly reclaimed land, where wheeled machines could not operate at all. The half-track could pull heavy plows through boggy soil, cross marshy fields, and maintain forward motion where other tractors simply bogged down. In forestry, drainage projects, and land reclamation work, it proved exceptionally capable. The engineering quality was high, using sealed bearings, robust drive sprockets, and hardened track links designed to survive harsh conditions. Yet this technical brilliance created practical problems. The roadless tractor cost far more than a standard Fordson. The track assemblies required specialist knowledge to maintain, with careful attention to alignment, tension, and wear. Spare parts were not commonly stocked by rural dealers, and field repairs were far more complex than replacing a tire. On roads, the tractor was slow and awkward. Steel tracks were noisy, uncomfortable, and damaging to paved surfaces. Transporting the machine between distant fields became a logistical challenge. Most importantly, only a small minority of farmers actually needed such extreme capability. As tire technology improved in the 1950s, wider profiles, lower pressures, better rubber compounds, ordinary tractors became far more capable in soft ground. For most farms, good enough traction at a much lower price made more economic sense than owning a specialized half-track machine. The Fordson Roadless did exactly what it promised. It worked. It solved a real problem. But it solved a problem that too few farmers truly had, at a cost and complexity that agriculture could not justify on a wide scale. It became a symbol of engineering excellence and practical misalignment, a machine that proved what was possible but not what was sustainable. Number 2. International Harvester Electrall System, 1954. By the early 1950s, rural electrification was transforming life on farms. Barns gained lighting, milking machines became electric, and workshops filled with motors and power tools. International Harvester believed that tractors should be the heart of this electrical revolution. In 1954, the company introduced the Electrall system, a tractor-mounted generator driven by the power takeoff shaft. With this attachment, a tractor could produce substantial electrical output in either single-phase or three-phase current, effectively turning it into a mobile power plant. The concept was genuinely advanced. Instead of owning multiple small engines to run augers, saws, pumps, or feed grinders, a farmer could use one central power source. The tractor could be driven to a remote location and supply electricity where no permanent wiring existed. In theory, Electrall promised efficiency, versatility, and modernity. The generator units themselves were robustly built, capable of delivering industrial-grade power. They reflected International Harvester's deep experience with heavy machinery and electrical equipment. In practice, however, the system conflicted with everyday farm reality. Running a tractor for hours purely to generate electricity consumed fuel and tied up the most valuable machine on the farm. If the tractor was powering a grain auger, it could not simultaneously be plowing or hauling. Many farmers already had fixed electric installations that were cheaper and simpler. Others preferred small standalone engines that could be dedicated to a single task without immobilizing a tractor. Equally important was familiarity. Farmers were accustomed to mechanical systems, belts, shafts, pulleys. Electrical systems were still new, and to many, intimidating. Troubleshooting wiring faults or motor problems felt risky compared to tightening a belt or replacing a bearing. Moisture, dust, and rodents made electrical equipment seem fragile in harsh farm environments. The Electrall was not unreliable, nor poorly engineered. Its problem was conceptual. It asked farmers to reorganize how they thought about power. Instead of adapting to existing habits, it attempted to replace them. Most saw little advantage in changing systems that already worked. As a result, sales were limited, and the Electrall quietly disappeared from catalogs. Decades later, the idea of centralized power generation on farms returned in the form of modern generators, inverters, and renewable systems. The Electrall proved that International Harvester's vision was sound. But in 1954, the economic and cultural conditions were not ready. The machine became a lesson in how even correct ideas can fail when they demand a future that has not yet arrived. Number 3. General Electric Electrac E20, 1969. In 1969, when nearly every tractor relied on internal combustion engines, General Electric introduced something extraordinary: the Electrac E20, a fully electric tractor designed for real work. This was not a toy or a novelty. It was a genuine garden tractor, capable of mowing, tilling, plowing snow, and pulling implements. Powered by a bank of lead-acid batteries, it used electric motors for propulsion and implement drive, eliminating engines, gearboxes, and exhaust entirely. The Electrac embodied ideas that would not become mainstream for half a century. It was quiet, producing little more than a hum. It emitted no fumes. Torque was immediate and smooth. Maintenance requirements were minimal: no oil changes, no carburetor adjustments, no ignition systems. For homeowners, institutions, and light agricultural users, it promised a cleaner and simpler future. Technically, it worked. Within the limits of battery technology, the Electrac performed as designed. For mowing lawns or operating small attachments, it was capable and reliable. However, users expected it to behave like gasoline tractors. They attempted long, continuous workloads. They plowed heavy soil for extended periods. Under such demands, the limitations of 1960s battery chemistry became obvious. Lead-acid batteries were heavy and had low energy density. Runtime was limited. Charging required many hours. Cold temperatures reduced capacity sharply. When battery packs aged, replacement was expensive. To users accustomed to refueling in minutes and working all day, these constraints felt unacceptable. The tractor itself was not flawed. The energy storage of its era was. Electric drive systems were ahead of their time, but the supporting technology had not caught up. GE eventually withdrew from the tractor market. Today, electric tractors reappear using lithium-ion batteries, advanced motor controllers, and fast-charging infrastructure. Everything the Electrac represented is now technologically viable. In hindsight, it was prophetic. But in 1969, it demanded a future that did not yet exist. The Electrac became an industry mistake, not because it failed, but because it arrived before the world could support it. Number 4. Allis-Chalmers Experimental Power Shift Tractor, 1950s. During the mid-20th century, tractor transmissions were simple, mechanical gearboxes. Changing speed required stopping, clutching, shifting, and restarting. Under heavy load, this broke momentum and wasted time. Engineers at Allis-Chalmers sought to eliminate that inefficiency by experimenting with what would later be known as a power shift transmission, a system that allowed gear changes under load without disengaging the drive. Using modified tractors as testbeds, Allis-Chalmers developed experimental machines that employed hydraulic clutch packs and internal gearing to permit smooth speed changes while pulling implements. For plowing and heavy tillage, the benefits were immediate. Operators could adapt to soil conditions on the move, maintain traction, and reduce fatigue. In principle, it was a revolution in tractor operation. The difficulty lay in the era's manufacturing and service environment. Hydraulic systems in the 1950s were still evolving. Sealing materials wore quickly. Contamination caused internal damage. Machining tolerances necessary for long-term reliability were expensive to achieve. A failure inside the transmission required major disassembly, far beyond the capabilities of most farm workshops. Agricultural machinery of the time was expected to be repairable with basic tools and local knowledge. Farmers depended on simplicity. A tractor that could not be understood or serviced outside a specialized shop represented risk. Dealers lacked training, spare parts networks were not prepared, and warranty costs threatened to become unsustainable. Allis-Chalmers recognized that although the system worked, the agricultural world of the 1950s could not support it. The concept was shelved. Only decades later, when materials, hydraulics, and service infrastructure matured, did power shift transmissions become common across the industry. By then, competitors led the field. The experimental Allis-Chalmers machines proved the future of tractor drivetrains. They also demonstrated that innovation without ecosystem readiness becomes a burden. The technology was correct. The timing was not. Number 5. Massey Ferguson Brown. Type A, 1933. In 1933, when most tractors were little more than motorized replacements for horses, the Ferguson Brown Type A introduced a completely new philosophy of agricultural engineering. Designed by Harry Ferguson in partnership with British engineer David Brown, this tractor was built around a revolutionary idea. The tractor and its implement should function as one integrated unit. Instead of dragging tools behind it on a drawbar, the Type A used a hydraulic three-point linkage that lifted, positioned, and controlled implements as part of the machine itself. This system fundamentally changed how power was applied to the soil. As resistance increased, when a plow hit hard ground, for example, the hydraulic linkage automatically transferred weight to the tractor's rear wheels. This increased traction and stability, preventing wheel slip and maintaining depth without manual adjustment. Implements could be lighter because they no longer needed their own wheels and frames. The tractor became more efficient, safer, and easier to control. In engineering terms, it was a breakthrough on the scale of the internal combustion engine itself. It solved long-standing problems of traction, implement control, and operator fatigue in one elegant system. Nearly every modern tractor today is built on this exact principle. Yet the Ferguson Brown Type A was a commercial failure. The tractor entered the market during the depths of the Great Depression. Farmers had little capital. Many struggled simply to survive. A machine that cost more than conventional tractors and that relied on unfamiliar hydraulic systems appeared risky. Rural mechanics were trained on simple mechanical linkages, not pumps, valves, and precision seals. Dealers did not yet understand how to demonstrate its advantages effectively. Farmers are pragmatic. They invest in what they understand. The Type A required them to trust an invisible system. Oil under pressure, over chains, and steel. Many hesitated. Competing manufacturers, threatened by the new concept, ignored or dismissed it. As a result, only a small number were sold. Ironically, when Ferguson later partnered with Henry Ford, the same three-point system was introduced on the Ford Ferguson tractors at a price and scale farmers could accept. The idea conquered the world. The original machine that proved it, however, faded into obscurity. The Type A was not wrong, it was visionary. But it asked farmers of 1933 to adopt a future they could neither afford nor fully understand. It became an industry mistake not because it failed technically, but because it demanded transformation during an era that could not sustain it. Number 6. Big Bud 747. 1977. The Big Bud 747 remains the largest agricultural tractor ever built. Constructed in 1977 by Northern Manufacturing for the Rossi brothers in California, it embodied the extreme edge of mechanized farming. With more than 1,100 horsepower from a 16-cylinder Detroit diesel engine, it stretched over 50 feet in length, weighed more than 100 tons, and rode on tires taller than a man. It was designed to pull massive deep tillage implements across vast fields in a single pass. From an engineering perspective, it succeeded. The tractor delivered exactly what it promised: unmatched pulling power and productivity for enormous operations. It reduced the number of field passes, covered immense acreage quickly, and proved that there was no theoretical limit to tractor scale. Yet it also revealed the boundary between engineering and practicality. Big Bud could not travel on standard roads. Bridges, gates, and transport regulations all became obstacles. Moving it between fields required special planning and equipment. It demanded custom parts, specialized maintenance, and highly trained operators. No ordinary dealer could stock components for a one-of-a-kind machine. More importantly, it fit only a handful of farms on Earth. Most operations, even large ones, found that using multiple smaller tractors offered flexibility, redundancy, and lower risk. If one machine failed, work could continue. When a machine the size of Big Bud stopped, everything stopped. Economically, it made sense only in a narrow window. Enormous contiguous land, specialized deep tillage, and owners willing to accept unique logistics. That combination was rare. Only one was ever built. Big Bud demonstrated that raw power alone does not define progress. Agriculture is shaped by roads, transport systems, repair networks, labor availability, and financial risk. A machine that ignores those realities becomes a monument rather than a model. It was not a failure of engineering. It was a failure of integration with the world around it. Big Bud proved what was possible, but also proved that possibility is not the same as practicality. Number 7. John Deere Model R Diesel, 1949 to 1954. When John Deere introduced the Model R in 1949, it marked a historic turning point. It was the first diesel-powered tractor widely marketed in the United States. In Europe, diesel engines were already gaining traction, but in America, farmers still relied almost entirely on gasoline, kerosene, or distillate engines. Deere's engineers recognized diesel's advantages long before the market did: superior fuel economy, massive low-end torque, and long engine life under heavy load. On paper, the Model R was everything a modern farmer should want. Technically, the tractor was impressive. Its two-cylinder diesel engine produced strong pulling power at low RPM, making it ideal for heavy field work. Fuel consumption was dramatically lower than gasoline tractors performing the same tasks. Over a working season, the savings could be substantial. The engine was built for longevity, capable of running thousands of hours with proper care. In an era when farmers depended on their machines for survival, durability mattered. Yet the Model R unsettled its audience. Diesel technology felt foreign. Starting procedures required preheating and careful technique. The engine was loud, vibrated heavily, and produced a sharp industrial exhaust note, unlike anything farmers were used to hearing in a field. Many associated diesel with ships, factories, and locomotives, not with family farms. Fuel availability created another barrier. In many rural areas, diesel was not readily sold. Gasoline was everywhere. Diesel was not. Farmers hesitated to adopt a machine that depended on a fuel they could not reliably obtain. Mechanics also lacked diesel training. Repairing injectors, pumps, and compression systems demanded new skills and tools. A gasoline engine could be understood by nearly anyone with mechanical sense. A diesel engine seemed mysterious and risky. As a result, sales were modest. Farmers admired the efficiency, but feared the unfamiliar. It took another decade, along with the expansion of diesel fuel infrastructure and the rise of diesel trucks, for attitudes to change. Once mechanics became trained and fuel became common, diesel tractors rapidly became the industry standard. The Model R had proven the future. It was not flawed. It simply arrived in a culture that had not yet accepted industrial technology as part of everyday farming. Deere was correct, but early. The tractor became a stepping stone rather than a breakthrough, remembered as the machine that showed what was coming, but could not yet be embraced. Number 8. Case steam traction engines. Late 1800s, early 1900s. Long before internal combustion tractors existed, companies like J.I. Case brought industrial power into the fields through steam traction engines. These towering machines combined boilers, pistons, gears, and massive steel wheels into mobile power plants. They could pull multi-bottom plows, haul heavy wagons, and drive threshing machines through belt pulleys. For the first time, farms could access power on an industrial scale. Steam traction engines were engineering marvels. They produced enormous torque at low speed and could operate continuously for long periods. In an age when most labor depended on animals and human strength, these machines transformed productivity. A single engine could replace dozens of horses. They became symbols of progress, drawing crowds at demonstrations and fairs. But steam demanded an entire operational system. A traction engine required constant water supply, fuel in the form of coal or wood, and skilled operators. Boilers had to be managed carefully to avoid catastrophic failure. Warm-up time could take hours. Most engines required a crew, not a single operator. Maintenance was continuous: cleaning tubes, checking pressure, managing scale buildup, and inspecting riveted seams. As long as no alternative existed, these burdens were accepted. But when internal combustion tractors appeared, the contrast was stark. Gasoline tractors started quickly. One person could operate them. They required no boiler inspections, no water wagons, and no fire tending. They were lighter, cheaper, and easier to move on roads. Steam engines were not inferior in raw capability. In heavy pulling, they often outperformed early tractors. What doomed them was complexity. They belonged to an industrial environment where crews, fuel depots, and maintenance schedules were normal. Farms did not operate that way. Within 2 decades, steam vanished from agriculture. Engines that had once represented the pinnacle of power became relics. They were too demanding, too slow to prepare, and too disconnected from the emerging rhythm of modern farming. The Case steam traction engine did nothing wrong. It delivered exactly what it promised. But it represented an era where farming tried to imitate industry. Internal combustion tractors redefined agriculture as something different: lighter, faster, simpler. Steam became a symbol of power without practicality, proving that even greatness can become obsolete when the world changes around it. Number 9. FMC, Self-Propelled Bean Harvester, 1950s. In the decades after World War II, agriculture faced a growing labor problem. Hand-harvested crops such as beans required enormous manpower at precisely the same time every year. In regions where beans were grown commercially, entire seasonal workforces were assembled just to pick, strip, and collect pods before weather ruined the crop. Food Machinery Corporation, FMC, a company experienced in industrial and military equipment, believed this inefficiency could be solved with a single machine. The FMC self-propelled bean harvester was designed to do what human hands had always done. It moved through rows, lifted the plants, stripped the pods, separated the beans, and collected them in one continuous operation. It was not a crude adaptation of existing equipment. It was a purpose-built machine with conveyors, shaking mechanisms, separation systems, and a dedicated chassis. In mechanical terms, it was remarkable. It reduced labor dramatically and increased harvesting speed. Where dozens of workers were once needed, a single operator could now perform the same task. Technically, the machine succeeded. In fields suited to its design, it performed exactly as intended. It delivered clean beans, reduced harvest time, and made large-scale bean farming possible in regions where labor costs were rising. From an engineering standpoint, FMC had solved a real and difficult problem. The problem was that it solved only that problem. Most farms were not single-crop operations. They rotated fields, grew multiple products, and adapted each year to market conditions. Buying a large, expensive machine that served only one crop created financial risk. If the bean harvest was poor, the machine sat idle for a year. If market prices changed, the investment became a burden. Unlike tractors or combines, which could be used across many tasks, the FMC harvester had a single purpose. Maintenance added another layer of difficulty. The machine's complex internal mechanisms required specialized parts and service knowledge. Outside major growing regions, dealers were unfamiliar with it. A breakdown during harvest could idle the entire operation, and repairs were not always immediate. Farmers prefer versatility. They invest in machines that can earn their cost back across many seasons and tasks. The FMC harvester demanded that the farm revolve around it rather than serving the farm's broader needs. In the end, the machine became a specialist tool used in narrow contexts. It demonstrated what mechanization could achieve in crop-specific harvesting, but it also revealed the economic danger of over-specialization. The FMC harvester was brilliant engineering applied too narrowly. It proved that solving one problem perfectly can still be a mistake if the solution cannot adapt to the unpredictable nature of farming. Number 10. Hesston Early Self-Propelled Swather Prototypes, 1950s-1960s. Before self-propelled harvesters became common, cutting and windrowing crops such as wheat and alfalfa required tractor-towed equipment. This method worked, but it involved multiple machines, more labor, and limited efficiency. Hesston engineers envisioned a different future, a single, integrated machine that could cut, convey, and lay crops in windrows without a tractor. Early Hesston self-propelled swathers embodied that vision. They combined engine, drivetrain, cutting header, and conveying system into one unit. In theory, they reduced labor, improved crop handling, and allowed harvesting to proceed faster and more precisely. They were the ancestors of every modern self-propelled harvester. In concept, they were perfect. In practice, they were fragile. Hydraulic systems of the era were still developing. Drive components struggled with vibration and load. Early gearboxes and pumps were not designed for the continuous stress of field work. Breakdowns were common. Reliability during harvest is not optional. Weather windows are narrow, and every lost hour risks crop quality. Farmers quickly learned that an unreliable machine during harvest could cost more than it saved. Dealer networks were another weakness. Most rural service shops were equipped to repair tractors, not integrated harvesting machines with complex hydraulic circuits and proprietary components. Spare parts were limited. Training was scarce. When a prototype swather failed, it often sat idle for days. Cost also mattered. These machines were significantly more expensive than pull-type equipment. Farmers compared the price with familiar methods and asked a simple question: why risk everything on something unproven? As a result, adoption was slow. Many farmers waited. They observed. They allowed others to experiment. Only later, when hydraulics improved, materials strengthened, and support networks matured, did self-propelled harvesters become reliable enough to dominate agriculture. The idea was right. The early execution was premature. Hesston's prototypes showed the future of harvesting. They also revealed that agriculture cannot tolerate uncertainty at critical moments. A machine may be revolutionary, but if it fails when the crop is ready, it fails completely. These early swathers were not bad machines. They were machines born before the ecosystem around them was ready. They became industry mistakes not because they were wrong, but because farming could not afford to wait for them to grow up. These machines didn't break. The world around them did. They proved that being right too early can be as dangerous as being wrong. Innovation doesn't always win. Sometimes it waits.